Alright, okay, welcome back everyone. So today is our pleasure to have Kevin and Lee, who will be talking about algorithmic compression via pretrained neural networks.
Yeah, thank the organizers for inviting me here. So today I'm going to present some of the results that I've been had the pleasure to be working with this whole team here. A lot of the work have been done also with people who left the team, and Onion Ross and Greg Gelaton. So this review basically summarizes all the work done in that period, which was my first 2 years at the moment. So I have to say I'm still a newcomer to the field. So if you have a lot of questions, especially on the theory side, I'm happy to take them. But probably if I won't be able to answer, please bear with me. So this is the layout. So I'm going to introduce some of the background knowledge a lot of people here are familiar with. And I'm going to, and then the sort of the last third of the talk will be a topic called optimal steering, which is mentioned in the review, but I'm going to go into a little bit more depth into that. So I come from a background which is more aligned with the approximate inference field, and working in this in the last 2 years. Made me realize that actually this is not too far away from algorithmic equation theory. And also I think both of them are related to generative AI, which is popular these days. So as I understand, so AIT we're trying to do some level induction, or part of the goal is to infer what the real program of the world is. And this is a latent variable, essentially in the approximate inference land. So there, what we're trying to do is to come up with a summary of each data point in the data sets, for example, images. And the programs, or like the latent variables, they're not necessarily interpretable as a program in level induction, but essentially they're latent descriptions of data points or observations we have. And so from like approximate inference field, people are trying to generate data, which is an old approach, I guess, not so old approach to generative models. But then they're not too far away from diffusion models these days. And AIT is obviously trying to infer, given streaming online data, what is the real program most likely that's generating, or the distribution of programs that can generate the world. So today, what we are doing for pre-training a large scale models, regardless of text or images, it's incredibly simple. Well, the theory, at least the theory part of it, we get a data set of a distribution psi. And this is given a task label, or like a label of the data set. For example, you're training on movie reviews, or you're training on video data. This tau can be labeled for the data set, or it could be more complicated. So you know some specific structure of how data is generated, you can also embed that in. So the tau is a latent description, or like feature or sentiment, and then we draw essentially data from this traditional distribution sign given the tau. And then we just construct a predictor, however big they are, and we minimize the log loss, right? So this is essentially the recipe that's driving current search in AI. So this loss is also related to this is written in the form of an autoregressive model from left to right. Diffusion models, or discrete diffusion models that work on tokens, have any other flavor to this. But then I think all of these different variants are essentially trying to minimize upper bounds on this object, or basically this object itself. I'm not going to talk too much on fine-tuning or human preference alignment. A lot of the work is carried out under the pre-training distribution, so pre-trained models. Okay, so we want to essentially build a big model to this, but we don't really know what is the best predictor. Right? So this is, I think, in deep learning, we just delegate that to SGD, come up with flexible architectures. But really, there is this holy, sort of golden standard. Sorry, before going back, so basically, there's this also minimizing the loss function also gives you this compression result, which is that if we denote the marginal distribution over the observations x by mu, which averages out all the latent variables, then we can say that minimizing the log loss is equivalent to the compression, and we can also measure the regret measured basically, which is basically we can take it as a KL divergence, or just a difference in the log vectors under the different model, under the model or under the true distribution. And I think this is all the basics. People here are all very familiar with this. So I was talking about how do we construct this model, but essentially this Solomon induction gives us the real the best solution possible. So we want this neural network family pi theta to be large. But I think what we don't have explicitly in deep learning is preference for simplicity, which is an Occam razor that a lot of people have this preference towards. I think it is natural to have this preference towards simpler latent variables or simpler programs. So Solomonov prior over all computable programs, if they're binary, can be written as this form. So it's basically the probability is equal to the it's basically the log probability is equal to the negative length of the program length. So this is a prior we have on the program. So shorter programs have higher likelihood. And then the probability of given sequence under each program, let's say so given a program P, the probability of a sequence X is measured as basically it's a sum. So this is averaging over all programs. So summing over all possible programs, the likelihood is basically summing the prior probability mass of all the programs that can generate a sequence that starts with. This is n of X is the likelihood under the Solomon prior, and we measure the probability mass just by summing all the probability masses. Ideally, if we can, so this is a likelihood, and we want to maintain a posterior over all possible programs P, and we get more data. So this is the goal. So we have all possible programs in our bag. I just need to, after our belief, which one is more likely to generate our data. And it has this very nice convergence guarantee that essentially this total squared Hellinger error over all time steps is summing to infinity is bounded by a constant. This constant is finite, so that means all the future prediction errors measured in this distance has to go to 0. So this is a very nice property. So we can show that this is the case for Solomon induction. But does the current practice have that limit? It's unknown based on the neural architecture, neural network approach to prediction or to compression. So I talked about Solomon induction. I also talked about the recipe of how we train large models these days. But it turns out there is a unifying perspective to all of this, which is called the memory-based meta-learning perspective. So the meta-learning is it's a name invented more recently. The memory-based meta-learning came out from from a lot of emphasis was doing deep neural networks. Okay, so the task there is to say, okay, I don't really have a single task. I'm going to sample a task from task distribution side, which is basically like our label, like feature distribution. And then in the supervised learning setting, okay, so given a task, whether it's given human body height, predict weight, or given altitude, predict atmospheric pressure or temperature. So these are different tasks, and we're going to draw, two sets of data, which is the context of query C or Q. And in the context, what we're going to do is we want to train the model, condition the model such that it can predict the context Y. So given XC, we're going to predict YC. And then we're going to test this on a new query, okay, a new XQ, and with the target being YQ. Okay, so this is like the supervised meta-learning framework was how this was framed, and so what people have been doing in the past, at least in the deep learning literature, is basically to minimize the loss on the query label given both the context and the query input. So this is a loss function that's exists for a long time, and we can really turn this. I mean, this is really slightly more complicated in terms of notation to essentially next token prediction. We can take all the conditioning as the previous sequence, and we just predict the next token. So this is we can treat all of the sequence. For example, we can treat sequence of different lengths as different tasks. So this is like another T, which can be essentially a label now. And we can do this, and then we can show that actually that with more training, if you want to minimize the neural predictor, given the history you want to predict next, if you keep doing that, under very ideological or like a perfect mode specification and optimization capabilities, this should converge to the sort of non-parametric target, which is under the data distribution mu. What is my next token given the the history. And this can be written, as the sort of the posterior average of the predictive distribution. So this is so what the memory-based meta-learning or meta-learning field as a whole, they're trying to do is to approach this target from purely supervised setting. We don't need to compute this posterior. Everything is sort of the posterior is sort of hidden in the neural network base. And although it's less satisfying that we don't really have a direct access to tau, but for the experiments I'm going to show you that we can actually identify representations that look like a posterior. So essentially, if you just keep doing this next token prediction as has been done in meta-learning or in Solomon induction, which is also predict the next token, the goal. Also, the best predictor for the next token, we can achieve this sort of amortized Bayesian predictor where we don't actually have to compute the posterior and we can approach the best predictive distribution. So this is sort of my view of how, I guess, large-scale pre-training and Solomon induction, how they can be viewed in essentially the same recipe and same framework. So the sort of the latent variables on the two sides are in the large-scale training, you have different data sources or different features, and in Solomon induction, it's just program P. They have different priors, so the training mixture, I would say, is a prior over the latent. It's like a prior over the latent variable, and for the Solomon induction, you have the simplicity prior, which is missing from the large-scale pre-training. And then the sort of the notion of a likelihood in large-scale pre-training is this data likelihood, or basically the data given each task. And then in Solomon induction, my feeling is that this essentially we want to have an indicator function whether this program can generate the observed data x quantity. So this is sort of, and then we can have the posterior and predictive distributions, which are very tightly related, and also so basically large-scale pre-training is not too far away from Solomon induction, right? Except for some of the built-in simplicity prior, and also people are really in Solomon induction, people are trying to come up with very clever solutions to control the prior and the likelihood, such that the posterior becomes tractable and we can do the prediction. And in large-scale pre-training, we're saying, okay, let's not care too much about posterior per se, but just do prediction as well as possible. And we have the toolkit to do it these days, which is why it's really sense. Okay, so this is the recipe we're doing. Okay, so we're given a task tau, we draw data and minimize the log loss. And the claim here is that by more training, we can approach, the neural predictors, if they're powerful enough, if the optimizer is powerful enough, we can approach this sort of the ideal predictor on the true distribution. There are many examples that prior work that have shown that that's really the case. Sort of if you train the data for long enough by drawing many tasks, many data, you can really achieve similar effects as rigid regression or in-context learning. So these are people have been talking about in-context learning coming will give you a very nice Bayesian predictor. But there are also counterexamples. So if you take a pre-trained transformer sequence predictor, there are cases where the prediction don't behave in a Bayesian consistent way. And here is one example, but there are also many literature showing that non-Bayesian behavior of neural networks. And you could say that, oh, this is just because we haven't trained the model for long enough, or we don't have the right architecture. I guess we don't have a consensus yet. The current model behaves in a spectrum at the moment, and it's really a really nice research question to dig into why or where the Bayesian link is loosened by the practice. Okay, so this is, I guess, the whole overall theoretical framework is essentially we're saying, given in-context learning, we can train a neural predictor to achieve an ideal Bayes predictor. And are we taking questions as we go or at the end? Okay, if any questions, I think it would be a good point to pause or happy to go back to a few slides. Yeah.
What do you mean by it's sort of violates the Bayesian?
Yeah, so for example, I think there are many cases. So you can check the Bayesian consistency using you can give a sequence of I guess that's L, and then you're gonna draw continuations from that. So the posterior should average out to the prior. Posterior over the average posterior, given all the sequences, should average to the prior distribution. But then I think that doesn't hold for neural predictors. And there are also so if your data sources have some exchangeability properties, and neural networks can't learn that. That's like another sort of non-Bayesian, like less ideal scenarios neural networks. So I think there are also many interesting. So essentially, neural network verifications of whether the predictions are Bayesian is really hard to do because we don't have the ground truths. But a lot of literature basically is taking, okay, if it's Bayesian, then it has to be consistent in some sense under the Bayesian umbrella. It doesn't have to always be, okay, the posterior is, the weight, the normalized prior times likelihood, which is super hard to normalize practice. But there are other, behaviors of the base predictor that we can draw. We can test on neural networks whether they are satisfying the base from different angles instead of just computing the true posterior distribution. Okay, so from now on, it's going to be pretty much empirical verification. What we're doing is essentially take it's a neural network with different architectures. Could be recurrent neural networks, transformers. We just want to test, what the standard practice in deep learning, whether these architectures are sufficient for us to see if they're approaching the Solomon limit. Right? And we're going to test the trained model on the same task or test them on slightly different distributions just to see if, whether they generalize in a way we would expect from Solomon induction. We will compare the base predictor performance, compare with the neural predictor with the base predictor in terms of log likelihood or regret. And additionally, we'll also show some visualizations of the internal representations. So how they behave like a base predictor. And we're going to, this is sort of the ladder of complexity. We're starting from really simple binary IID, sort of conditional IID sequences, and then move on to, and then gradually towards the universal programs for approximate Solomon essentially approximate Solomon with neural networks. So, okay, so starting very simple. So let's say we draw the task, or the task is from a uniform distribution between 0 and 1, with beta 1, 1. And given that tau, we're going to draw conditionally IID Bernoulli point flips. Okay, so this is, I guess, the simplest possible binary distribution we can think of. And it's quite interesting that previously when I give talk like this, I get questions from the audience that your tokens, your X are all independent. How can you make predictions? And I'm like, yeah, I said conditionally independent distribution. Apparently that concept is not very well baked into the knowledge base of deep learning people. So obviously, of course, you can predict. Okay, you can just basically the best solution is you start with 0 and 0, and then you count how many zeros and ones you've seen so far, and that becomes your the parameters into your posterior, which is in a beta distribution with the parameters. That's the counts, right? So that's pretty obvious. So the question is, can we train neural networks to do it? To essentially mimic, to achieve this ideal predictor, right? So I think what's interesting, okay, this is a simple enough task. However, bear in mind that the neural network has only been trained to minimize the loss. It's never been trained to do any counting. There's no instruction for the neural network to count zeros and ones. It has to figure out a solution based on the log loss it's used to train. So whether the neural can do it or not, there's no guarantee in there. And what we found is basically we're going to skip the performance, right? I mean, this is such a simple task. There's no question that the neural network can do it. But what's interesting is that on these two architectures, LSTMs and transformers, what we did was say in the LSTM, we took the hidden activations or like the cell states, and we just did a simple PCA, principal component analysis, and took the first two PCs. And we could see already this tree structure that really resembles the ideal solution structure on the left. So each node here is so basically these trajectories are drawn by feeding in many sequences of zeros and ones. And so this point here is just the one input, it's node input, and here is one input, one token, one binary token, 0 or 1. And then so this is a tree with longer sequences. You can see that the nodes are pretty obvious for the cluster pretty well for the earlier sequences, and they become less sort of less well connected or less well clustered for longer sequences. But at least this kind of tree structure is kind of really interesting, and this has been discovered back in 2019 by Pedro Ortega, and we sort of extended to transformer architecture, where there's no real latent states in the transformer. What we did was we essentially take the output of the attention layer. So there's no intrinsic counting mechanism, or like there's no memory in the transformer, but we're just taking the activation after the attention layer as a proxy for the latent state. And we still see this kind of architecture. And what's interesting is if we don't train the networks, and just do when someone may ask, this structure just comes out from you're feeding in zeros and ones, does that give you that structure automatically? And the answer is no, it doesn't really give us this tree structure, especially for transformers. We don't really see any sort of pattern at all. So this really comes from training the network on this kind of data set. Any questions so far? Okay, good. Okay, so that was very simple, Bernoulli, traditionally Bernoulli IID, and we sort of progress along the complexity axis, and we are drawing a particular prior, which is essentially giving you piecewise stationary Bernoulli data geometry. So essentially, let's imagine we have a sequence of lengths. So this particular prior is known as the partition tree weighting, and proposed by Joe Bannes as a sequence predictor framework. But it has has this data generation process that basically splits the sequence into segments. Okay, so let's imagine if there are if you have only 4 sequence positions, the generation process randomly splits this into one of these configurations. Here is split in half, so 1 and 2 are the same segment, 3 and 4 are the second segment, and you can split this segment further to 1, 1. So the first is their own segment, and then 2 is their own segment. So this is like basically chopping up a sequence into different segments, and for each segment, we're going to draw a bias tau 1, tau 2, tau 3, etc. So each segment has its own unique bias, and the exact solution. So basically, this is the prior for the journey process. The posterior, how we update the mixture, how we update the breakpoints, essentially, or like the segmentation, involves a very complicated and elegant solution. That's in this paper, so it'll be Joe's paper. But again, as we said, so if we're training neural predictors, we don't ever need to do this posterior inference explicitly. We just sort of train it to do the prediction on this data set, and in the end, we want to see whether neural networks can learn this elegant, very complicated solution that properly inverts the journey process to get the posteriors to make predictions. So here is one example. So here, each vertical dotted line is a segment sampled from the data generator distribution. So here, the whole length is 256. So we split it one in half here, and then another time half here, and another half here. And so each of the segment has its own bias, denoted by the solid line here. So this is the mean, and then here is also the mean for different segment. And so we have the best possible sort of the ideal posterior distribution in red. So PW is the predicted probability of that the next token is 1 or 0. So if it's 1, then it's goes up. And consider the red line is essentially overlapping with the LSTM predictor as trained for a little. That's sort of after training. And we can also measure the regret and sort of cumulative regret over time compared. So we can see that so these two lines are overlapping, and there's a line here which is sort of doing better. This is because it's sort of cheating with basically it's a KT oracle predictor with the bias known given to the KT predictor. So it's like I know what the bias is. So this is the best possible thing. But here really the important bit is so these two lines are really overlapping. Just shows that neural network can do essentially can approximate the solution in this case pretty well. And then we move on to context tree weighting, which is slightly different than, which is much more complicated than the position tree weighting. And so, and the essence, the sort of gist of it is that it's a variable order Markov generative process. It's sort of the dependence changes as sequence gets longer. And again, here we compare between the CCW prior, which is in blue, with the transformer, which is large scale transformer, the large transformer we tried. And yeah, again, they overlap quite a lot. So at the end, that of course neural network is only approximate, so it won't be exactly the same as the CCW proper sphere. And then here we can do a comparison between different architectures and different scales. And you can sort of see in this case that transformer has the best performance on all scales, and also yeah, and compared to other architectures, and the best predictor for the large scale as well. So essentially, this is essentially the RNNs are not so good for the transformers. And even if we augment the recurrent neural network with a stack or like some memory capabilities, they can do a bit better, but still they're not as good. So these are sort of custom architectures we built with RNNs augmented with memory. So again, transformer nail the task, and other networks architectures they can approach by increasing the scale, but yeah, not as good as transformers. And then we moved on to this universal prediction. So previously we've been doing binary sequences or Bernoulli binary sequences or PTW or CCW priors. We can argue that they're not universal, they're not so good, right? So the properties are sort of the way the segment distribution will not be so flexible. Then so here we're really going for this. Let's try to really be serious and sort of really approach the Solomonov bound the domain where we are going to actually simulate a Turing machine. Okay, so in this case, we're using so constructing a computable and normalized universal Turing machine. So here is like a one word summary of the whole paper, a lot of technical contributions. So essentially, we took the BrainFog universal Turing machine and then and made it such that it's computable and normalized, and then we bias. So so this is sort of a trace of the Turing machine, how it works. It takes 7 symbols, and they can operate over. You have this kind of operations. So what we are going to do is to essentially draw all possible programs and then simulate the data that's output by the Turing machine. So the input is going to be one of the 7 symbols, like string of 6 symbols, and then we just take the output. Okay. If we do it, in a naive way, we won't be able to generate interesting programs. So we found a way to sort of bias the program distribution, which we call Q, to produce interesting to be the interesting ones that produce good, interesting outputs. And at the same time, we can prove that by biasing the prior distribution, the universal Turing machine is still universal. So essentially, we are taking the Turing machine as a simulator of programs of data that's taking different programs, and in a field of in science called physics informed ML or like physics informed deep learning. This is what people do: take a physics engine and then they produce outputs, and hopefully these programs will constrain the model to think the way that will conform to the simulator. And yes, so this is essentially the whole framework. Any questions here? I guess.
Yeah, just one question. Interesting. You mean just 0, 0, 0, 0, 0?
Yeah. So like interesting means that so it won't be. So basically, there are certain operations that cancel out in the operation in the stack. So we'll get our biasing will remove the boring sequences. Yeah, and then so basically the way we did it was very simple. Actually, we just had a order 2 Markov model. So like given a context of 2 symbols, I think what we did was we simulated all the possible. We draw from the prior, a uniform prior, and then we simulate the Turing machine. We take the output, sort of have a few criteria and just select which ones are interesting, and then we took those program that has interesting outputs, and build a order 2 Markov model to predict what the sequence is. Yeah, so essentially it's a very simple way of constructing less boring first. And then I think we managed to increase the likelihood of generating interesting program by close to 100 times. So basically it's a more interesting program. Otherwise it'll be all zeros. Okay, so this is essentially the result. Okay, so now the Turing machine is properly complicated. So the fact that but then we don't have a, as in 6W or PTW, we don't have a golden standard of the prediction. So the comparison won't be, compared to the best possible predictor. So here what we have on the left is the cumulative regret in bits. And so here we have basically the different scales. And again, the transformer is doing really well compared to other architectures. And the large models have the lowest regret. I think that's interesting to know. I mean, transformers somehow they're really suited to all these patterns we've seen so far. And so there are some caveats in the paper. Essentially, the transformer will generalize a bit less to longer lengths. But within the training lengths, transformers is sort of the best. And on the right, we have the accuracy, meaning how well we can predict the next output from the Turing machine. And they're all pretty good. I think they're all sort of approach the ceiling here. There's a slight improvement on there, but it's not really visible here. And so here is the main result that we have. And next, if we are so this is basically training on the Turing machine data, predicting on the same data set. But then there are other tasks. We want this to be universal, right? So we have to test it on other data sets. So this is a generalization test, essentially. So we can evaluate the trained model on 6W, and or on some tasks that are called Chomsky tasks, which is like revert strings or closing brackets for closing different levels of parentheses. And so on the left, on 6W, again, the best possible predictor is here, and the models trained on the universal Turing machine data, they're much worse. But then still we can see a little bit of a sign of scaling or the architecture. Interestingly, LSTM generalizes better than transformer, which is like interesting result in this sense, I think. And then on the right, we have again the accuracy, which basically much difference. And on the Chomsky tasks, we have a baseline here, but not here. So basically, the Chomsky tasks have there's an average over different Chomsky tasks, and then the mean accuracy is this line. And we can see there is a meaningful, like non-random generalization to these tasks. Especially for transformers, now they're really generalized better in this sense. So it's kind of really surprising that somehow I think, yeah. So I guess not surprising in the sense that the Turing machine will be able to include programs of any of these generative processes. So, but the fact that the neural predictor trained on the data set can generalize here, that is a slightly non-trivial result.
Any questions? It's one bit about the small, medium, large. What is kind of sizes are you?
Yeah, they're not. I think they're sub-billion essentially. They're not large to today's standards. I forgot the actual scale. I think we did something different. So they definitely differ in terms of multiple one-fold and two-fold.
Because actually we were talking earlier on about how small, like a small like data object, whether any of these kind of methods are useful. I mean, CGW, for example, can handle 100 bits or like really small objects, right? But is there any of this relevant for really small things like that, or is it still in the billions?
So it's small in sense.
Small in like the training data that you're giving.
Oh, okay.
Yeah. So like CGW, you can give it 100-bit string and ask it to predict the next bit. But can you do something as small as that with these kind of methods?
Small test data. It was essentially inference the data for inference, right? So for running the model forward. Then here we use all possible training data, and then we just fit in. Yeah. So like this is definitely not on a large data set scale. Right? Okay, so we've seen so far that so essentially on the different problems we've shown that the neural network trained by log loss, they tend to, I think that we definitely see a sign that they converge to choose the best possible base optimal predictor. And we've evaluated this sort of the claim on a range of problems from the scale, essentially, you can see. And on the smallest problem where we can, we have this internal, we know what the true posterior should look like, especially, and we can show that internal representations of the neural network, they really resemble the tree structure we saw. And we also saw that at the end that there's non-trivial transfer from UTM data to Chomsky tasks or to CTW data sets. So that's very interesting analysis. Okay, so we've done those are just toy scale problems. We've done a lot of scaling to to approach the real data regime and see whether what this framework can do. Compression, loss loss minimization, what can we compress, right? or what can we achieve? So this is, I guess, sort of one of the most popular work we did before, which is take seriously the compression view. And what we do is we train a model, we take a pre-trained model on chinchilla. It's 70B parameters, trained on 1.4 trillion words. So, and we test this, we basically use this as the compression models for basically take the lodges and use them to use the arithmetic compression arithmetic coding to give us the compression bits. And we measure the length of the given image, what is the length of the code. Okay, so that's really taking on the compression view. So we see, okay, so the chinchilla was trained only on text. So on this text domain, we can see that is if we don't count the model size, this is the sort of the compression ratio we can get, which is a lot better than the generic purpose compressors. This is an interesting finding. So this means that we can all do better. So if the sort of the compression and decompression algorithm have access to chinchilla, we can really compress them a lot. But then if we adjust for the model size, it's crazy. So this is not a question. So because 70B is pretty manageable. But I will show you smaller models later. Okay, on images, we can also see some really interesting generalization. So this is completely surprising to me. If we believe that chinchilla was only trained on text, this level of compression is clearly so surprising or astonishing to me. But yeah, so this is pretty cool that we can actually compress both image and audio using a model that's trained on text. So that's
how are images and audio represented? How do you give that to the model?
I don't remember exact details, but I think we give them the
sequence of RGB bytes.
I think it's the bytes. These are the raw bytes. Yeah, I think that's the raw bytes we're using. We don't use any. So it's still bytes. So it's not using the whole vocabulary size of the transport. That's So basically something that's not human readable. Yeah. So this is cool that we can and then later on we did a study where we trained smaller models, and basically we tuned the model size to find the best models to find the best sort of adjusted compression ratio, and basically if we evaluate, so if we train this figure here shows that the training domain, so different training data, audio or audio plus image or audio plus text, and if then evaluated on audio. So this is saying, yes, training on audio is still the best. It achieves the lowest compression ratio, and it's already on par, or at least better than some of the domain-specific compression algorithms. And this is again training on different combinations of data and then evaluating images and text or all data sets. So I think all cases are sort of agree that training on one domain is the best for that domain, except for this case where we found that training on audio and image does slightly better on just value on images. Yes, this is an interesting finding. So image and audio can go have a little bit of synergy, although not too much. Yeah, so essentially this is the proper compression ratio, right? So it's sort of accounted for the model size. And this is sort of the model size we had from 1 million to 20 million. So they're small, I think, to my standards. So here we can see that for the for audio data sets, you can find the sweet spots. We sweep over the context size, so we're not the transformers has finite context window, and the context window will determine the amount of compute, and also another factor that will determine the compute will influence the compute is the model size, the number of parameters. So here is a very interesting sweet spot here for some context window lengths. Okay, so that was compression on sort of the natural stimulus or like text. We also try to sort of compress a invertized planning in an agent that can do planning in its under the hood. So in this case, we're training. We take the Stockfish, which is a chess engine that can that has really good, very strong, essentially superhuman performance on chess games. And we take, so the model works as follows, but we'll do a lot of, they have a neural network inside, and Stockfish also does a little bit of tree search, look ahead to compute the value of each move of a board. Okay, so given the board, I'm going to tell you that the value, the sort of value between 0 and 1, whether I'm going to win or not, or like I think it's basically the value for the board. And we basically train a transformer to distill the Stockfish engine. And it's surprising that we can actually train the transformer to play chess to a reasonably standard. So this is a model we have in the end, which is better than AlphaZero, but then not as good if we turn on MCTS for AlphaZero. And obviously it's going to be worse than Stockfish because this is where the data is coming from. But still, I think the field of chess was slightly surprised by this in the sense that there's a single transformer predictor that can play chess without any planning. So essentially, the fact that the transformer can distill a planning agent, Stockfish, which is Stockfish, is a very interesting finding. And yeah, so there's no test times research or no test time reinforcement. So basically take the predictor and then we act according to the predicted value for both moves. Yeah.
Yeah, so but isn't this how AlphaZero also works? Doesn't it also distill from its own research? Until it sort of converges.
So I think so I think that's so Alpha is training from its own gameplays. But here we're sort of cheating a little bit with just take whatever the Stockfish's predictions is, Stockfish estimate of the value is. So we're not using any. So we take the data, like data generator from the Stockfish.
But from your sort of intuition, I guess you did run the experiment directly. But if you did this on AlphaZero, would the transformer converge to the AlphaZero policy, or would it do better than the AlphaZero policy? But
I think it will. It won't. I think it's. I don't think it will beat the AlphaZero, but I think it will approach on below it. It's similar to behavior here. Right? So here we're just taking the Stockfish behavior, not the AlphaZero, and we're comparing with AlphaZero.
So then I sort of descend that conclusion that AlphaZero should have had a transformer rather than.
I think AlphaZero is very different. So I think it's more advanced in terms of how the way it's trained to. So I think it's much more clever in that sense.
Okay.
I think when AlphaZero came out, Stockfish wasn't around. So Stockfish was sort of post AlphaZero, so it's an older technology. So here, previously we showed that transformers can compress data and generalize, and here essentially an example of is stealing a planning agent. So there's no planning, and then it's still example free run. Okay. The remaining time, so this is some slightly more recent work we did in this kind of using pre-training model to investigate how the real sort of language model modality is operating. Here, instead of pre-training, okay, so it's a change of flavor, right? So we would take a pre-trained model, and our goal is not to say we're going to infer the program of the world or to build the most powerful AI in general. Here, the goal is to say, okay, we're given some predictor, maybe the SI, the best predictor we can find, but now we want to condition it or prompt it, to fine-tune it towards a specific task. I think this is very relevant these days because now people are doing a lot of harnessing, which is a very advanced version of prompting. And before 2024, all the language models are really bad at understanding human prompts. So this is the fact that we've gone so far with the harnessing and all the system prompt design just means that this is a very active research field, at least open question how we prompt a powerful predictor. And our approach again is to go to the very basics, the fundamentals, and ask ourselves how can we steer a predictor of a conditionally IID Bernoulli sequence predictor. And so here, so now we're given a predictor. Now we're saying, okay, our predictor has been trained on this mu, right? All possible tasks and binary sequences. That's all we had before. Now there's a task Q, which is a Bernoulli sequence given a particular value of tau1, which is we don't know. So we don't. Yeah. So let's say we know the value of tau1, but then we want to prompt a predictor to behave like this distribution. And we can take neural predictors or base predictors. We can tell do some empirical analysis on how easy or how hard it is to steer them. And for example, if we're doing prompting, what we are trying to do is to say, okay, let's take the best possible predictor we have, the closed form, and then we're going to minimize the log loss on the task of Q, but then we're only gonna minimize this over a set of conditioning sequence of length up to L. Okay, so this is basically I think one of the simplest possible prompting setup we can have, and we can also replace the mu with a neural predictor or approximate predictor, which are transformers these days, and we can see whether how much we can achieve the best prompting under the ideal predictor or compared to the task itself. And there's a typo. So we're gonna compare the loss with the best possible base predictor. So we mentioned a log loss under the Q under itself. So this is like the entropy of that task distribution. So this is a loss function for prompting where we optimize the sequence as conditioning signal. So there are various versions to this. We can constrain these sequences to be binary tokens, but they can also live on a simplex, so probability space. So instead of 0, 1, so instead of one hot, we can relax the constraints to make them, probability distribution that sum to 1 instead of being 0, just 0 and 1. There's also we can also do them in the weight tuning. So we can also optimize this with a little bit of a weight tuning, we call WT. But today I'm going to focus more on the prompt tuning, where we can hard prompt tuning, which is basically optimizing over binary sequences, or we can do simplex prompt tuning, where the sequence is constrained to simplex, or the real values. There are no constraints, they're just the real values. And again, so let's see when the tuning or prompt tuning can work well or should work well. Let's say we have been pre-training the model on the, again, 0 and 1 tau range, so between the bias between 0 and 1. And then the task is a tau sub 1 is a particular value here. Then we think that this case, we should be able to prompt it because we can figure out the ratio. We feed in the empirical ratios, and then the beta distribution should converge towards this delta distribution with more sequence. That should be no surprise here. And then indeed we find that so comparing different prefix tuning methods or hard prompting or whatever binary tokens. And so this is the target. So this is the target-based predictor. There's no regrets because this is the basic itself. It's just a single Bernoulli bias. And we can see that even a finite number of tokens, we can prompt it to these values, and then soft prompting can really close the gap. Right? So soft prompting, what soft prompting does is to essentially optimize the embeddings. So here they're all minimized sort of on the input space. Here we are minimizing the embeddings of the inputs, and we can really close the gap to 0. We're really closest to that. But then what? So the fact that there's some regret here just means that the amount of parameters that we are tuning isn't sufficient enough. Maybe so. This is using 6 tokens to prompt, optimizing prompts of token length 6. But we can if we increase the length of prompts, ideally they should converge to the delta function tau1. But then there's another situation where prompting, I guess, even with infinite number of tokens won't help you too much, which is to prompt towards a mixture task. Okay, so we've been pre-training on a uniform distribution between 0 and 1. Now let's say the task Q is also like the training distribution, except that the bias are supported on tau 1, tau 2, two discrete values. And in this case, any kind of prompting sequence will push the prior towards a delta distribution, which won't approach the mixture distribution here. So this is a case where we think that tuning won't work so well, and empirically we find that's the case. So in this case, the best possible predictor has a loss of 0.61, which is just a log 2. Basically, there are two possibilities, and then the slow prompting is much worse compared to before. So all the prompting methods couldn't really close the gap. So this is like an intuition that we had coming from, but intuition we have coming from just analyzing the base predictor behavior under two task distributions, and our findings seem to suggest that at least with hard prompt it won't work so well, but the fact that even soft prompting didn't work so well is sort of an interesting finding that's consistent with our hypothesis coming from analyzing just binary sequences. And we can also have on the visualization. So it's sort of on the top we have the transformers, and on the bottom we have for the LSTM. Okay, so these kind of prompting, at least on LSTMs, we see that the prompted state, so this circle is like a state after the prompt, they tend to stay on the task space, let's say, and also hard prompting, and they all sort of give you a point on the tree. But then if we are taking a transformer and we prompt it, and we won't be able to, we don't really see that the prompted states are still in the tree space. So this is sort of saying that if we're prompting a transformer with a continuous value, such as if it's a real valued vector in the input or like in the embedding space, then the transformer sort of goes into a regime where it's far away from the training constraints and will behave in a sort of less predictable fashion. So, okay, and then there's also some further work we did to understand why prompting is really hard. So previously we were also tuning, let's say, we could tune the prompt towards a certain task, but then we didn't really see what the prompt is. Right? So here, so my statement that the prompting is powerful but unintuitive just says that why there are so weird prompts that work so well, and then sometimes the best prompts, even if we see them, they don't really make sense. And let's just go back to the case again. Let's say we're given a binary sequence predictor that takes only zeros and ones and spits out zeros. Now the question or the task is, well, can you prompt it to generate 70% ones? Okay, so a lot of humans, I guess, many people here will say 70% ones will give you 70% ones out, but then that's not really the answer. So the answer depends on the pre-trained distribution side. So if there are only, let's say, we have seen before that if the training distribution is uniform between 0 and 1, then you should be able to find the right proportion of, you should fit in the zeros and ones with the right proportion with respect to targets. But now if we only have 2 points, like if the training distribution only has 2 possible points, 0.2 and 0.7, then it turns out that the best prompt in this case, you should fit in all ones, because that just concentrates the posterior towards the 0.7 mass. So that's, I think, one very simple case to show prompting perhaps it isn't so intuitive if you only know a downstream path, but not the pre-trained distribution. So pre-trained distribution is really okay. Thanks. So this is like the simplest case we can show, and then so I'm gonna jump a few steps. But then what if the task is only 0.6 between 0.2 and 0.7? And in this case, we can show that the best prompt visualized on the sort of 2D plane in terms of counts of zeros and ones, they really don't have very intuitive pattern. So it shows that if your task is outside your pre-training support, you're going to get really even more strange or even weirder prompts. So this is basically, we also verified some of the findings on the large scale language models, where we sort of use IMDb as a data set. And the finding essentially here is saying that the best prompt usually contains a single word. So sometimes we think that giving it more information in the prompt should help the model should steer the model better, but that's not always the case. The best prompt turns out to be just a single word, so positive or negative. And we also have an example in the paper of how we studied in-context learning with RL. Okay, so I'm gonna summarize here a little bit. So we've said that if we collect all possible data sets as we do in training frontier models, we can do meta learning on it, and then with enough training, we can close the gap, the approximation gap. So that will give us the amortized learning predictors. But then there are really two. I think there are two problems that will stem from it. One thing is how do we best steer it? So if we're given a task without knowing all the Pretrained distribution, or how can we steer the model in a good way? And as a sort of a hint we saw before that the level of difficulty here is correlated with what kind of distribution you use here. So this is currently invisible. So if there are ways to help us understand the training mixture, that would be really valuable. And another branch which I didn't touch on, but will be covered by I think later talks, especially by Pedro Ortega tomorrow, also on Wednesday. Yeah, so he will be talking about ways to sort of close the causal gap. So how can we use a predictor to make to think about making decisions where the observation, the actions won't affect the posterior distribution. So essentially we just take a predictor and let it act in the world. It will suffer from delusions that I think a lot of people here are aware, and then also Pedro Ortega will talk about. Yeah, okay, that's I think the talk today, and final questions.